Can philosophy make you a better programmer? This is a full course on data structures and algorithms, explained through real philosophy with real citations. Every data structure is a way of organizing thought. Every algorithm is a philosophy made executable. Arrays are memory, trees are categories, recursion is a strange loop, sorting is justice, and graphs are connection itself. From Plato's forms to Descartes' method to Hofstadter's paradoxes, the history of philosophy contains every idea you will ever need in computer science. This course covers arrays, linked lists, recursion, trees, binary search, graphs, hash tables, sorting, big O, divide and conquer, dynamic programming, greedy algorithms, Dijkstra, and heuristics. 16 chapters. Real sources. By the end, you will never look at code the same way again. Why do we need algorithms at all? Plato argued in the Republic that behind every particular thing stands a perfect form, an ideal version that the real world only approximates. An algorithm is a form made executable. It is the perfect procedure, the ideal sequence that any machine can follow. When you write a sorting algorithm, you are not inventing order. You are pointing at the perfect form of order and saying, follow this. Plato believed the forms are eternal, unchanging, and more real than the messy world we see. Computer scientists believe the same thing about algorithms. The code rots. The algorithm endures. The array is the simplest data structure, and it maps to a question philosophers have asked for centuries. Where is memory? John Locke, in his essay concerning human understanding, argued that the mind is a blank slate, a tabula rasa, filled by experience. He compared memory to a storehouse where ideas are kept. An array is exactly that, a storehouse with numbered rooms. Every element lives at an index, a fixed address you can jump to instantly. Locke worried that memories fade and decay. Arrays have the same problem. Fixed size, fixed order, and when you run out of rooms, you must build a bigger house and move everything. Heraclitus of Ephesus taught that everything flows. You cannot step into the same river twice, because the water is always new. The linked list is the Heraclitean data structure. It has no addresses, no index, no instant access. Each node points to the next, like stepping stones across a river. To find anything, you must walk the whole chain, one node at a time. This seems inefficient, and it is. But the linked list can grow forever, because it does not need a fixed block of memory. It embodies the philosophy that the world is not a storehouse, but a flow. Order is not given in advance. It is discovered by traversal. Recursion is the strangest idea in computer science, and Douglas Hofstadter explained it best in his book Gödel, Escher, Bach. He called it the strange loop, a system that reaches upward and finds itself. A function that calls itself is a strange loop. It is the Ouroboros, the snake that eats its own tail. To compute the factorial of n, you call factorial on n-1, which calls factorial on n-2, until you reach the base case, the ground of the loop. Hofstadter argued that self-reference is the root of consciousness itself. The mind is a recursion that somehow observes itself. Every time you write a recursive function, you are programming the structure of thought. Aristotle organized all of knowledge into categories, and his system in the categories is a tree. Genus at the top, species below, individuals at the leaves. A tree data structure is Aristotle's ontology made concrete. It has a root, which is the most general category, and children, which are more specific, and leaves, which are the particular things. Every file system is a tree. Every family tree is a tree. Every taxonomy of living things is a tree. When you build a tree in code, you are doing what Aristotle did in 350 BC. You are saying, the world is not a flat list. It is a hierarchy of kinds. Binary search is the Socratic method. Socrates, in Plato's dialogues, never gave answers. He eliminated false beliefs one at a time, cutting the space of possibilities in half with each question. Binary search does exactly this. It starts with a sorted list, checks the middle, and discards half of the remaining candidates. Ask, eliminate, repeat. In logarithm time, you find the answer. The Socratic method is binary search applied to beliefs. Instead of examining every idea, you test the middle one and discard everything worse. This is why Socrates was dangerous. He could find the hole in any argument in a handful of questions, the same way binary search finds any element in a handful of comparisons. Gottfried Leibniz dreamed of a universal characteristic, a language that could express every truth and resolve every dispute by calculation. A graph is the closest thing we have. Graphs are everywhere in his philosophy. The monads are isolated, but their relations form a network. In computer science, a graph is nodes and edges, cities and roads, people and friendships, web pages and links. Stanley Milgram's 1967 small world experiment showed that any two Americans are connected by about 6 steps. A graph is the map of that connectedness. When you model a social network, you are building Leibniz's universe, where every point is defined by its relations to every other point. Hash tables are the memory palace. The ancient art of memory, described by Cicero in De Orator, involved placing ideas in imaginary rooms so you could recall them instantly. A hash table does the same thing. It takes a key, runs it through a hash function, and jumps straight to the right room, without searching anything. Lookup time is constant. This is the closest computer science comes to magic. But there is a cost. Collisions happen when 2 keys land in the same room. The memory palace has limited rooms, and when 2 ideas arrive together, you must handle the crowd. Perfect memory, it turns out, requires clever handling of conflict. Sorting is the imposition of order, and Zeno's paradoxes show why order is philosophically strange. Zeno argued that motion is impossible because to reach the finish line you must first reach the halfway point, and before that, the quarter point, forever. Aristotle replied by distinguishing actual infinity from potential infinity. A process can pass through infinitely many stages in finite time if the stages shrink fast enough. Sorting algorithms embody this. Merge sort splits the list in half, again and again, down to single elements, then merges them back in order. The total work is n log n, a finite number that hides an infinite-looking process. Big O notation is the philosophy of infinity made measurable. It tells you how fast a process grows as the input grows, and it is the closest thing computer science has to a law of nature. Divide and conquer is Descartes' method, straight from his discourse on method in 1637. Descartes proposed 4 rules. Never accept anything as true that you do not clearly know. Divide each difficulty into as many parts as possible. Think in order, from the simplest to the most complex. And review everything to make sure nothing is omitted. This is exactly merge sort. Divide the problem, conquer the parts, combine the results. Every recursive algorithm that splits a problem in half is Descartes' method running on silicon. The French philosopher who doubted everything gave us the single most productive technique in computer science. When you divide and conquer, you are a Cartesian. Dynamic programming is memory applied to time. Henri Bergson, in Matter and Memory, argued that memory is not a dusty archive. It is active, creative, and it exists to serve the present. Dynamic programming stores the results of subproblems so they are never computed twice. It remembers the past to avoid repeating it. The classic example is the Fibonacci sequence, where naive recursion recomputes the same values endlessly. Dynamic programming says, write it down once and reuse it. There is a philosophy of wisdom here. Those who forget the past are condemned to recompute it. The person who remembers what worked and what did not moves forward without repeating their mistakes. Greedy algorithms are utilitarianism. Jeremy Bentham, in his introduction to the principles of morals and legislation, argued that the good is the greatest happiness for the greatest number and that every choice should be calculated by its consequences. The greedy algorithm makes the best choice at each step, hoping local gains add up to a global optimum. Sometimes this works. The coin change problem, with standard coins, is solved greedily. But Bentham's philosophy has a famous flaw. Maximizing each moment does not maximize a life. Greedy algorithms can fail when a locally optimal choice leads to a globally terrible result. The traveling salesman cannot be solved greedily. The lesson is ancient. The immediate pleasure is not the same as the good life. Bentham's calculus and the greedy algorithm both need a longer view. Dijkstra's algorithm finds the shortest path through a weighted graph. Seneca, in his letters to Lucilius, taught that foresight is the mark of wisdom. The wise person considers consequences before acting, chooses the path with the least suffering, and plans the route before beginning the journey. Dijkstra's algorithm is Seneca's foresight made formal. It explores paths in order of total cost, and the moment it reaches a node, it knows it has found the cheapest way there. This is rational planning under uncertainty. Every navigation app runs a stoic philosophy. The shortest path is not the obvious path. It is the path chosen by careful, cumulative reasoning about cost. Seneca would approve. Heuristics are the wisdom of shortcuts, and the science of them comes from Herbert Simon and Daniel Kahneman. Simon coined the term bounded rationality in 1955, arguing that humans cannot consider every option, so we use rules of thumb. Kahneman, in Thinking Fast and Slow, called these heuristics System 1 thinking, fast, automatic, and mostly reliable. Heuristics trade accuracy for speed, and they usually work, but they produce systematic errors, which Kahneman called biases. In algorithms, a heuristic is a solution that is not guaranteed optimal but is fast enough. The A-star algorithm uses heuristics to guide search. The lesson is deeply human. Perfection is expensive. The wise person knows when to be exact and when to be good enough. So what does all of this mean? Algorithms are not just procedures. They are the physics of thought. Every structure in computer science was anticipated by a philosopher. Plato dreamed the algorithm. Locke dreamed the array. Heraclitus dreamed the list. Aristotle dreamed the tree. Descartes dreamed divide and conquer. Bergson dreamed dynamic programming. When you study data structures, you are studying the accumulated wisdom of 2,500 years of thinking about thinking. Plato, in the allegory of the cave, said the programmer's job is to see the forms behind the shadows. That is what an algorithm is. A form, extracted from the chaos of reality, made precise enough to run forever.